What's up, my advanced math peeps? Here's what we've got going on today. We just finished up our last unit, and so we're going to start this new unit all about series and sequences. And so the first thing we're going to do today is just get a background for what a sequence is and some terminology that goes along with that, like the terms of a sequence, the index of a sequence, the general term of a sequence, some of those things. So let's start to get into that just a little bit. Now, I wanted to talk real quick. I didn't write anything down about this, but I want to talk about what a sequence is because it really is still a function. We still have inputs and outputs. We input the number term we're on, and we output a result as a result of whatever our formula, our function is that says what to do with that. The thing that's different from a normal function that we talked about in a sequence, the input has to be whole numbers. You can't input decimals, which means if you were to graph a sequence, it would actually just be dots. It would be points. Whereas if you graph a function, you can connect those points with a smooth curve because all the in between the whole numbers works. On a sequence, it does not. It's just the whole numbers. So let's see if we can come up with some terminology that goes along with the sequence. And so when we have a sequence, the way we're going to talk about the terms of a sequence, we'll use an A. And so A sub 1 means the first term. So in this case, whatever this sequence is, the first term is 5, is what that's saying. And whatever number term we're on is referred to as the index. So the index is just first term, second term. The index is that number term we're on. And then another big thing, if we say A subscript n, this is the general formula for how we get the terms. And so A sub n is what we call a general term. So in this case, we do 2 over whatever number term we're on. So that means the first term in this one would be 2 over 1. The second term would be 2 over 2. So n refers to inputting whatever number term we're on. So that's going to help us do this first example. So find the first 4 terms of this. So our general formula is right here. A sub n equals n plus 1 over 2n. So that means it's going to be 1 plus 1 for the top over 2 times 1 for the bottom for the first term. Do you notice what I did here is basically everywhere where there is an n, I input 1. And so to find the second term, we're going to do the same thing, except now the second term is every place where there's an n, we're going to input 2. And so we've got 2 plus 1, that's 3, over 2 times 2, that's 4. So in other words, we've got 3/4 for the second term. And then we can do the same thing for the third term. So for the third term, we've got 3 plus 1 over 2 times 3. And so in other words, that's 4 over 6, or to simplify a little, that's 2/3. And then for the fourth term, every place where there's an n, we're going to input 4. So we've got 4 plus 1 over 2 times 4. And so in other words, this one comes out to 5/8. And so there's the first 4 terms of that sequence. All right, so that's what we do to find the terms of a sequence. It basically just input n where it needs to go in the general formula, and that comes up with the terms. Now I have another example of the same thing here, basically. I put something interesting in this one, though, because this is something that happens quite often in sequences, and so I wanted to give us some exposure to something that looks like this. And so this very first part says -1 to the n plus first power. Here's what that's going to make happen if we think about it for a second. -1 raised to any odd power comes out as -1. If I do -1 times -1 times -1 3 times, it's negative again. -1 raised to any even power comes out positive. -1 times -1 to the second power comes out as +1. So here's basically what's going to happen. This is going to make that sequence go back and forth between positive and negative, and just that pattern forever. Or depending on what we put after it, it could go positive, negative, or it could start negative and go negative, positive, negative, positive. That depends on what we put in the exponent here. So in this case, let's just figure it out. Let's worry about the signs first, and then we'll worry about what this does in just a second. So for the negative and positive part, if I put in 1 in this sequence, -1 raised to the 1 plus 1 power is what this would say. If I raise it to the 1 plus 1 power, it's squared. So -1 raised to the second power is positive. And so this one's going to be positive, but you wouldn't have to write the plus sign. I'm just going to do it for like emphasis, kind of. And then if I put in 2 in this first part, negative 1 to the 2 plus first power, so negative 1 to the third power is what that becomes, so that's negative. And then the pattern is just going to continue, so that's positive, that's negative. And then we just need to figure out what this does to the sequence for the second part. So for the second part, we have 1 over n squared. So n is just whatever term we're on. So in this case, it's 1. So I have 1 over 1 squared, which is just 1 squared is still 1, 1 over 1 is 1. So this one I have negative because of what happened here, and then 1 over 2 squared. So that's going to be negative 1/4 in the end. And then here we've got 1 over 3 squared, and that's positive, so that's positive 1/9. And then this one is negative 1 over 4 squared, and so that's going to be negative 1/16. So there's the first 4 terms of that sequence. They alternate, and this is called an alternating sequence. That's the fancy name for this. And all that means is it alternates back and forth between positive and negative and positive and negative. All right, so there's the first part of how we find this stuff. Now, I wanted to kind of go the other direction. So you notice on these ones, I gave you the general formula, and you had to figure out what were the terms. Let's do 1 or 2 where I give you the terms, and you have to figure out what is the general formula. So this first one here, so example 3 part A, we have 1 over e, and we have 2 over e squared, 3 over e to the third, 4 over e to the fourth. Now, a really common mistake on these problems is to think about what did you do to the term before to get the next one. That doesn't matter. If we're looking for a general term, it's not based on the previous terms. It's based on where it is in the sequence. So we need to think about how is this related to the index, to what term we're on. So here n equals 1, here n equals 2, n equals 3, n equals 4, because it's the first term, second term, third term, fourth term. Do you notice the top number here is just whatever term we're on? That makes the top number be n for our nth term. So you notice our first term is a 1, second term is a 2, third term is a 3, and we're thinking about not how it relates to the previous term, we're thinking about how it relates to the index, to what term we're on. Now the bottom is e, and I didn't put a 1 here because it's just the first power, but it's really e to the first power. E squared, e to the third, e to the fourth. Do you notice whatever term we're on, it's e raised to that number? And so our general formula here on this one would just be n over e to the n. And so this looked fairly complicated at first, but as far as coming up with a general formula, that's actually a fairly easy example. It's just n for the top number over e to the nth power for the bottom number. A lot of times if you have a fraction that you're trying to figure out the nth formula for, a really good way to approach that is think of the top and the bottom as 2 separate entities. What is the formula for the top? What is the formula for the bottom? And then just put the one over the other. So just kind of think of them as 2 separate things that you're trying to find the formula of. Now, for part B, this goes 3, 7, 11, 15, 19. Now again, this is one where it's really tempting to say, all right, the pattern is add 4 each time. That's true, we're adding 4 each time. That doesn't tell us the nth term though. And so if we want to figure that out, we have to figure out how this is related to the numbers of what each term is in a sequence, or in other words, the index. So I need a formula that when I plug in 1, I get 3. When I plug in 2, I get 7. When I plug in 3, I get 11. When I plug in 4, I get 15. When I plug in 5, I get 19. That's what we're going for, a formula that relates what term it is in the sequence to that number. So this is a little harder. Now the fact that we're adding 4 each time does help us a little bit to come up with a formula that works, because if you keep repeatedly adding the same thing, repeated addition is multiplication. And so since we're adding 4 over and over and over again, the number term we're on is actually a multiple of 4. And I know these aren't multiples of 4, but they're just a little off from a multiple of 4. Now here, let me put this down for just a second. If I did 4n, 4 times 1 would give us 4, 4 times 2 would give us 8, 4 times 3 would give us 12, 4 times 4 would give us 16, 4 times 5 would give us 20. Now, do you notice this is not exactly what we want there, but it's not far off. Isn't this just one number bigger than everything we want there? And so the fact that we're repeatedly adding 4 means we would want to put the multiples of 4 across here, but then adjust this to where it needs to be. So that's 4n. I need to be 1 less than this, and so the formula for this one would be, if I just do 4n minus 1, that's going to put me at 3, 7, 11, 15, 19, the exact set of numbers that we wanted. All right, so hopefully that helps a little bit. That's the big thing that gets confusing is we're not relating it to the previous term, we're relating it to what term we are on in the sequence. Now, after I just made a big deal about that, the next thing we're going to do is talk about ones where they are defined by the previous term. Now, this is not always the case. If you have a general term like this, that's not the case. Now, there are some sequences, though, where the only way to define them is from the previous terms. Example 5 is one of those, actually. This one you could actually write a general term for. We'll see in just a second. But to have a recursive formula means it's defined by the previous terms. So to find a term, we actually need to know the term right before it, and in some cases, the two terms right before it. So in this one, we're going to try to find the first 4 terms of this. Now, do you notice I already gave the first term? You can't start a recursive formula unless you have a starting term. You have to have a number to start with. And so the first term is 1. And so we know it goes 1 something else. I want to talk about this part right here next to the 4. Because this is really where we have to start thinking about what this means. This says to find a term, to find the nth term, you do 4 times a, do you notice the subscript says n minus 1? So to put this in terms of like the second term, to find a sub 2, we would want to do 4 times, it says a sub 2 minus 1. I'm going to put the 4 in parentheses. A sub 2 minus 1, which is really a sub 1. Do you notice the subscript is where the 2 minus 1 is? So really to find the second term, this says do 4 times a sub 1. But don't we already have the answer for a sub 1? A sub 1 was 1. Now, a really good way to think about this, because you could put in all the numbers and do this every single time and you'll get the answer, but this is kind of annoying. So let's think about this logically, what this really says. If this is term n and this is term n minus 1, isn't this just the term right before the one that you're finding right now? Think about that for a second, let that digest. That's the index, so this is what term we're on. This is, the index is 1 less, so that means the term right before the one you're finding right now. So another way to say this would be to find a term, you do 4 times the previous term, 4 times the term right before it. And so if I do 4 times a sub 1 or 4 times 1, I get 4 for the next term. Now to find the third term, it would be 4 times the second term. It's 4 times the previous term, you could say, to get the next term. And so 4 times 4 gives us 16. And then, again, to find the next term, I do 4 times the previous term. So to find the fourth term, it would be 4 times the third term, or 4 times 16. And so that would be 64. So there's the first 4 terms of that sequence. All right. And I want to look at one more example of this, just because this is an interesting one. We're going to try to write out the first 5 terms of this sequence. Now, this one's even a little more involved. Do you notice the nth formula involves an a sub n minus 1 and an a sub n minus 2? And I'm giving you the first and second term both on this one to start with. So this says we don't need to find a sub 2, we already know it, it's 1. So the first one we'd really have to find is a sub 3. So to find a sub 3, we would do a sub 3 minus 1 plus a sub 3 minus 2. Or in other words, to find a sub 3, this is all in the subscript, we do a sub 2 plus a sub 1, just subtracting the 3 minus 1 and the 3 minus 2. But do you notice we know the answer for a sub 2 and a sub 1? They're both 1. So to find a sub 3, we would do 1 plus 1. So in other words, a sub 3 is 2. Now again, even though we can do it with all the numbers here, this gets really annoying if you have to keep doing this. So let's see if we can logically make a sentence of what this is saying to do. So to find the third term, do you notice I added the second term in the first term? So to find a term, if the subscript is n minus 1, that's the previous term. If the subscript here is n minus 2, that's the term 2 before it. So instead of the term right before it, go back 2 spots in the sequence to find the next one. And this is where it'd probably be easier to start writing it out like with commas like we did here. So our sequence goes 1, 1. We just saw the next one is 2. And so this really says to find a term, you add the term right before it and the term 2 before it. Or to put it in different words, to find a term, you add the 2 previous terms. So to find this next term, I would want to add the term right before it and the term 2 before it. And so I have 2 plus 1, so that would be 3. Then to find this next term, I'd want to add the 2 right before it. That's 3 and 2, so that's 5. And that's as far as I said to go here, but we could keep going with this. 5 plus 3 is 8, 8 plus 5 is 13, and we could just keep going with this. This is a fairly famous sequence. This is actually called the Fibonacci sequence. And this is kind of a famous sequence in mathematics, and one of the things that's kind of applicable to what we're talking about right now, you can define this sequence recursively. You actually cannot make one of these to come up with that sequence of numbers. It's impossible to make a general formula that gives you that exact sequence. You can come up with one that will give you numbers close and will round to the right number, but you can't actually come up with a sequence that will, a general formula that will give you that sequence. So that's kind of why recursively defined sequences exist, because there are some where making a general formula is just literally impossible. So that's the big things for today. So making a general formula, coming up with a formula for how to get the term based on its index, not what's happening with the previous terms. And then a recursive formula, that is when we are basing it on what's happening from the previous terms.